Every traditional software program is a blind machine executing a rigid, human-written list of instructions. It only knows exactly what we tell it to know. Take a common problem, building a program to filter spam out of your email inbox. This diagram maps out the traditional programming process. A human studies a batch of spam emails, identifies obvious patterns, like the word free appearing constantly, and manually writes a specific rule instructing the computer to block any message containing that word. But the digital environment fluctuates. Spammers adapt. They swap out a single letter, spelling free with the number 3, and instantly bypass that hard-coded rule. The spam gets through again. To keep up, programmers have to catch the new trick, write another rule, and add it to the stack. Over time, that list expands into an endless, impossible-to-manage web of manual patches. This reveals the complexity ceiling of traditional programming. When a task involves fluid environments or lacks clear mathematical boundaries, like recognizing human speech, relying on a human to manually write out every single possible rule completely breaks down. The bottleneck in computing is no longer hardware power. It is our own human capacity to manually script enough logic to capture the chaos of the real world. So what if instead of writing the rules, we gave the computer the data and asked it to deduce its own rules? That specific approach is the foundation of machine learning. Looking at this updated flowchart, the workflow shifts entirely. Instead of writing logic, we feed the system raw examples. We provide regular emails alongside flagged spam, a training set. The system ingests this to independently find hidden patterns. By shifting the burden of logic creation from the human brain to the machine, software can finally scale to the true complexity of the data it processes. The central mathematical engine doing that processing, the part of the system that actually learns and makes the predictions, is called a model. This taxonomy diagram breaks down models into 3 learning styles. Supervised learning predicts specific values based on labeled examples. Unsupervised learning hunts for hidden clusters and unorganized data. And reinforcement learning relies on trial and error, learning from mistakes. Returning to our spam filter, what happens when spammers change their tactics again? As this flowchart shows, the system features a built-in automated loop. It simply ingests the new incoming spam data, retrains itself, and updates its own logic. Because the system continually updates its internal parameters based on new information, it adapts to changing environments indefinitely, without a single human ever needing to rewrite the code. Because machines are no longer constrained by human-written rules, they can tackle massive, high-dimensional problems that were previously impossible to solve. This allows engineers to deploy models in high-stakes environments, detecting microtumors in brain scans, anticipating credit card fraud in milliseconds, and forecasting global revenue shifts based on thousands of variables. To handle massive visual and linguistic datasets like these, engineers use neural networks, complex, layered computing architectures that mimic the physical structure of the human brain. This diagram reveals the ultimate consequence. When a neural network solves a problem humans couldn't crack, it leaves a working solution. Researchers then inspect and reverse engineer that solution to see exactly how the computer reached its answer. By studying the machine's work, researchers uncover hidden variables and structural patterns in science and economics that we were previously completely blind to. Machine learning now acts as a sophisticated lens for research, providing the insights humanity needs to decipher the hidden complexities of our universe.